All right, we're ready to do today's lab, molar mass by freezing point depression. First thing you have to do, of course, is read the method. But after you do that, you need to decide what kind of data is going to be recorded during this procedure. And then you build your table, like I have here on the board. You build your table so that you have a place for every number that you're going to produce. Now, the theory behind molar mass by freezing point depression is that first, it's a colligative property. Freezing point depression is a change in temperature, here, a change in temperature that is experienced by a solvent from the pure solvent to the solvent that has some solute dissolved in it. And there will be a change in freezing point between the pure solvent and the combined solvent and solute. And that's what the delta T sub F is. And this formula says that that difference in temperature is equal to some constant that is characteristic of the solvent. In this case, the solvent is lauric acid. And this K is associated only with lauric acid. And if you multiply the concentration of the solute in lauric acid times this constant, it should be equal to the change in temperature that is experienced between the freezing point of the pure solvent and the solution. We'll talk about that a little more later. Let's get to the mechanics of the procedure. We're going to be doing actually two procedures. The first one, we're going to determine the freezing point of lauric acid. And to do that, we're going to heat it to a temperature of 70 degrees centigrade or above so that it liquefies. And we're going to measure the temperature as it begins to decrease from about 60 degrees to some point past its freezing point. And we're going to record the temperature in 30-second intervals. Okay, so I've set up enough positions in this table so that it should be enough to cover the entire range. Then we're going to repeat the experiment with the solution of benzoic acid in lauric acid as the solvent. And the freezing point depression means that the temperature, the freezing temperature, or that point at which the liquid now, with the benzoic acid in it, freezes, should be depressed. In other words, it should be a lower temperature. So we're going to start out at a high temperature, around 60 degrees, and temperature will gradually decrease. And since the freezing point of this solution should be less than the lauric acid, the pure lauric acid, then it should take longer for us to reach that freezing point. That's why this table has more places in it at 30-second intervals. Okay, so we've got our table set up there for the timing and temperature measurements. We also need to know what is the mass of the lauric acid and what is the mass of the solute, the benzoic acid. We need to know those two factors. And here is the constant that's associated with the lauric acid, 3.90 kilogram degrees centigrade per mole. Okay, so let's get to the method. It's relatively simple, and all that's required is a heated water bath, which has been on the hot plate now for several minutes. And we're going to check the temperature to see if it's warm enough to proceed. And it looks like it's greater than 70 degrees, which is fine. That will be sufficient to melt the lauric acid and to melt the lauric acid plus the benzoic acid solution afterwards. We need a large test tube, and this is not the same size, I don't believe, as in the method, so let's get a measurement. Notice it's clamped so that when we lower it into the water, we don't have to hold it there. All right, so what's the length? The length appears to be, oops, I got that turned around. Let's see. That is 150 millimeters long with a width of, not counting the lip, of course, with a width of 25 millimeters. So it's 25 by 150 millimeter tube. We'll put it back in the clamp. And then we'll use a separate thermometer to measure the temperature of the lauric acid in the beginning and the mixture afterwards. Okay, I also have a timer set up here. So these 30-second intervals are continuous. That is, once you start the timer, you don't stop it. You take a measurement every 30 seconds. And the time it takes me to go over to the board and write the value of the temperature should be 15 or 20 seconds. So very shortly, when I return, it'll be time to take another measurement. So this is going to go rather quickly. All right. The method now starts out saying that you need a 400 milliliter beaker with 300 milliliters of water in it. I like to have a little bit more room. So I've changed that to a 1,000 milliliter beaker, or 1 liter beaker, and I filled it with a little over 900 milliliters. The exact number isn't important. You just need enough water, and it needs to be heated. In order to keep the water from bumping, if you know what bumping is, if you heat something on a hot plate, and it has a tendency, when you near the boiling point, that the liquid will all of a sudden burp out some of its vapor. That's characteristic of just about every liquid. So in order to avoid that, we use boiling chips. These are just pieces of pumice, and you may or may not be able to see down in the bottom of that beaker are little boiling chips. What that does is it creates a nucleation site for the vaporizing liquid to gather in smaller amounts, so we don't get the big burp. We get little small bubbles. You may notice also that as the water heats up, we're generating gas bubbles. But I just measured the temperature at 70 degrees. It's not hot enough to boil, so where's that gas coming from? It's dissolved gases in water. Gases will dissolve in liquids, and when you heat them up, gases in a liquid become, for most gases in liquids, they become less soluble. So as you heat up the water, the gas comes out of solution as tiny bubbles. And all of that will have proceeded to completion. We will have degassed the water before we reach a temperature of boiling. Now I'm going to protect myself with gloves. Next step, we need to measure out a known mass of lauric acid, the solvent. So I'm going to use a weigh boat, and I'm going to get my spoonula, and we're looking for about 8 grams. I say about because it's not important that we get exactly 8 grams. It's important that we know exactly how much we measure. So, let's put the weigh boat in here and tell it to go to 0 again. So that subtracts the weight of the weigh boat, and anything we measure now is only the weight of lauric acid. By the way, lauric acid is a fatty acid. You may or may not know what that is, but all the fats in your body, the true fats, contain these fatty acids. There are various kinds. Lauric acid is one of them. But this is a purified version. Okay. It's doing quite a bit of bouncing around. Okay, I think it's stable now. So we're going to measure 8 grams and get the exact value. Okay. It'll take quite a bit. It's not very dense. And we're creeping up on it. Okay, now we're going to slow down. Here we go. Now I'm going to close the container, close the lid, let it settle down, and clean off my spoonula. I want to cross-contaminate any other reagents. Okay, now let's see if it's settled. 8.05. We're going to have to just pick a number because it's bouncing a little bit. 8.057. 8.057 grams. That is the mass of the solvent, lauric acid. Okay, now we need to transfer the lauric acid into the tube, and we want all of it, if at all possible, to end up in the bottom of the tube, because anything that gets stuck to the walls up here won't be heated. It won't be in contact with the hot water through the glass, of course, so it won't melt, and that will bias our results. So we use a funnel with a very wide mouth. It's called a powder funnel. That allows us to put large particle things through the funnel, but it also extends the bottom of the funnel down into the tube so that it's less likely for any of the particles to stick to the walls. It happens primarily because of static electricity. So there's our transfer. See, there's some dust, so we've lost some in the process. And let's rinse this out, because we may want to use it again. There we go. And we'll just let it dry here. Okay. So now, let's take something we can tap our funnel. There we go. And that also should be rinsed out. If we want to use it again, But we want to be sure it's dry before we use it again. Okay. Go. All right. So notice that there is some stuck to the walls. Now the less of that you have, the better. That's going to bias our results. That's called experimental error. We think we have 8.057 grams down in the bottom, melting in the hot water, but actually we have less. So what does that do to the concentration? If the denominator, which is the solvent, is less than we think it is, then the concentration of the solute later is actually higher than we think it is. All right, so let's start heating this. The water is sufficiently warm. Just lower it into, and we go as deep as we can, like this. And hopefully, we don't have to clamp it down really tight, just to stabilize it. And what we may notice, let's adjust that just a hair. Let's get the writing on this beaker out of the way so you can actually see inside the beaker. Now, we're waiting for it to freeze. And you can see it's gradually melting. And you can help it along with the thermometer, because this is the one we're going to use to measure the temperature. So what we'll do is stir that lump to distribute the heat, and gradually melt that lump. It's getting there. It's going to take a while. So let's see what the water temperature is. Just out of curiosity. This is not a data point. This is just to see, to satisfy my curiosity. Okay, water temperature is passing 80 degrees, on its way. 83, 5. Okay. So before long, that water is going to be boiling. And that's not a problem. We only need it to be hot enough to melt the solids in our tube. I see the lump smaller. Now it's 2 lumps. Now it's 3 or 4 lumps. Okay, we're getting there. So what are we going to do when it is melted? When we're satisfied that the lauric acid has been liquefied, we will pull the thermometer, the tube, and the clamp out of the water and move it away from the heat source. Let's take another close look. Yeah, I think it is completely melted. All right. Okay, so now we can lift this out of the water bath and move it around here away from the heat source. And now we're going to start watching. Let's see. Let me get my timer back. We're going to start watching the temperature. And when the temperature drops to 60 degrees, that will be our 0 point. In fact, if I start exactly at 60 degrees on my timer, then I can wait for 30 seconds and write both of those temperatures on the board. And we stir. Stirring continuously distributes the heat throughout. And by doing that, we know that the temperature we're measuring is the actual temperature of the substance in our tube. Okay, we're still coming down. All right, it's not time to start yet. We have to wait for the temperature to drop. We could start measuring now, but we'd take a lot of wasted measurements. The reason that the method says start measuring at 60 degrees is because the freezing point of lauric acid is less than 60 degrees, much less, in the 40 degree range. So if we start at 60, we have sufficient data without excess and wasted effort. Okay, we're on our way down to 70, still dropping. Okay. How we doing? 68. All right, we're getting there. Now, if I had a lab partner, I'd let my lab partner do the stirring, and I'd do the reading. Reading and recording. All right, we have 65 degrees. We're almost there. And the second it hits 60, I'll start the timer. You're probably wondering why I don't write this on a piece of paper right here and just stand here the whole time. Well, personal preference. I'm going to have to put it on the board anyway. There we go. 62, 61 and a half, we're almost there. Let's see, 61 and about ready to start the timer now. Okay, so when my timer hits, see if you can see that, when my timer hits 30 seconds, and from then on, every 30 seconds past that, we'll take a reading. That's 15 seconds. Okay, 25, 26, 27, 29, 30. And that's 57. Okay, so our first measurement was 60. Second one is 57. All right. So we're getting close to the next measurement. 58, 59, 60. That's 56 degrees. Okay. Now, another 30 seconds. And that's 54. .54. 2 minutes is the next one. Coming up on it in 10 seconds. And that's 52 degrees. Now, how do we know when we've reached the freezing point? Well, there are two methods. One is visual. You just observe when you start to see lauric acid crystals. And that's fairly reliable. Okay, here we come up on another 30-second measurement. Now, 50 degrees. And the other way is to plot your data. And I'll show you after we've gathered all our data what that looks like. Okay, another measurement, 48.5. Okay, I'm getting my exercise today. Coming up on another one. And this is 47. Now, I see some solid forming in there, but it's not forming in the liquid. It's splashed up on the walls of the tube. So that's not the freezing point. It has to occur inside the material. Coming up on another measurement right now. 46. We're getting close. Very close. Okay. Take a look at those numbers. Ready for another measurement soon. 10 seconds. And it's 44.5. I don't see any crystals yet. 44.5. Okay. Got something that looks suspicious in there. Okay, another temperature. 43.5. Okay. Yep, I think we're there. Yep, that's it. Let's keep taking measurements. So it's happened 43. So we can either take 43 or 43.5. One of those is the freezing point because it happened while I was over here marking the temperature. So we're going to keep taking the temperatures just to go past the freezing point. Okay, 43. Now, if we get 3 43s in a row, we'll stop. So that means we're definitely at the freezing point. Remember what I've said about freezing point and solutions. If you have, for instance, if you have ice in water, if you have ice and water there together, the temperature will not change. And that's true for any liquid, and it's frozen solid. 43. All right. We are at the freezing point. We can take either one of these. We don't need that value. Okay. So now what do? Well, the method says pull the thermometer out and wipe it off. But we don't want to do that the way it is now because it'll bring out lots of solid with it and we'll lose some of the sample. So we definitely have to be liquid again before we take that out. So let's heat it up. Yeah, let's heat it up and be sure that everything is soluble. Now, why do we have to take the thermometer out of there? I mean, it's just going to heat it again, right? Well, let me demonstrate. That doesn't work very well, does it? There's not room in there for the funnel and the thermometer both. So we're sort of forced to take the thermometer out. But I don't like to wipe off any of that material because that introduces an experimental error. So what I'm going to do is change the method. I'm going to let the thermometer drip, and then I'm going to set it in such a way, say on a beaker, so that it won't roll off. And notice these beakers have lips on them. So if I use this beaker properly, I can set this thermometer aside now that it's all liquid again. Just let it drip. And hold it out here long enough to solidify. There we go. It's not solid yet, but it's not dripping either. So if we set it down here like this, right? Now we've retained all of our material on the thermometer, and when we put it back in, there won't be any missing. Okay, so what do we need next? We need benzoic acid. Now the benzoic acid is the material for which we are trying to determine the molar mass experimentally. And we're using the freezing point depression to help us determine what that is. Now I'm going to show you how that works as soon as we get all the data. So let's get all the data and then we'll go back to the calculations. So the benzoic acid, let's see if this whey boat is dry. Yep, it looks ready. Let's get my spoonula out and our benzoic acid. This is pure benzoic acid. Now I mentioned colligative properties earlier, but I didn't really define what a colligative property is. When you do this lab, you should have been introduced to the concept of colligative property, and it's very simple. A colligative property is any property of a liquid, of a substance, that does not depend on the chemical nature of the substance. In other words, we could put anything that will dissolve in lauric acid. Benzoic acid, we could use a number of any other substances that will dissolve in lauric acid, and the only thing that matters is their concentration in lauric acid. It doesn't matter what the benzoic acid is. It doesn't matter that we use benzoic, or it doesn't matter that we use something else. The freezing point depression will still be the same based only on the molar concentration of the solute. So that's good to know, because suppose we don't know anything about the benzoic acid. Well, I mean, we don't know its formula. We don't know its molar mass. So we can't calculate a molar concentration based on what we know of the substance. We're going to measure that concentration based on this freezing point depression property. And then we can use that, first of all, to determine experimentally the molar mass of our substance. And if we were trying to determine the molecular formula for the substance, that would be one of the steps that we would perform. That's all I'm going to say about that right now. So, we need about 1 gram. We're going to add about 1 gram, but we're going to measure exactly how much we have. Okay. All right, it won't take much. I think it's a little denser than lauric acid. Yep. We went a little past, which is not a problem. So all we want is the exact concentration. Let that settle down while I clean off my spoonula. Just need a little bit. Here we go. All right. 1.190. 1.190 grams. Okay. Now, we got almost the data we need. Now we need to determine the freezing point of the mixture, the solution. And it will be different than this. In fact, it should be less than that. That's what freezing point depression means. We're depressing the freezing point from this point to something less. And then the calculation is the difference between those two. All right. Now, let me reset my timer. And there's our benzoic acid. All right. Let's take this out of the water for just a second. And transfer the benzoic acid. Notice how these weigh boats work. You can make a funnel out of them. You just squeeze the sides like that. That gives you extra control. I see a little bit more coming out of there. I get as close to quantitative as possible. Here we go. This is just plastic. I'm not going to break anything. There we go. We'll clean that up in just a minute. All right, now let's put it back in the hot water. And we can put our thermometer back in here, and notice it has solidified on the thermometer, but we're going to reintroduce that into the solution. Here we go. Water's starting to boil. I can see it. Now that's boiling. That's actually water vapor. That's not dissolved gases. That's converting one phase into the other. Okay, temperature. Yeah, we got a nice warm temperature. And let's see. You can see that it's going into solution. Yeah. In fact, I can see convection currents. What is a convection current? Well, it's a visual representation of one substance mixing in another one, but not quite mixed. It's on its way. And the visibility of that mixing is due to a difference in refractive index of one substance and the other. And that shows up easily with light shining on it. You have to go look up refractive index and you'll know what I mean. If you wear contact lenses or eyeglasses, then you are benefiting from refractive index. Almost there. Let's give it a minute. Okay. Yeah. There's a little bit left in there. I can see it. I don't know if it shows up on the video. There's a little bit that has not quite dissolved. A little bit of the benzoic acid that has not yet dissolved in the lauric acid. Let me give it a second. It's still rather warm. And you may be able to see, have to get the right angle, those little pumice chips are dancing around on the bottom of the beaker. That's because they're providing a nucleation source for the boiling water, making very small bubbles instead of one big one. Okay, I think we're all done. We can come out of the water now. Out of the water bath. Let's see. And swing it around away from the heat source. In fact, we can turn the heat off. Now we're going to do the same thing. We're going to watch it till it gets to 60 degrees and then begin our measurements. Okay, it's gradually cooling down. And we don't need the hot water anymore, so I've turned that off. And while I'm waiting for safety, I'm going to unplug it. Okay, temperature. It's 83 on its way down. Just have to wait. Patiently wait for this part. Now, when we get all our data, I'm going to go in here and take this pre-lab question and work out this pre-lab question, which is good for you because it's worth 5 points. So if you pay attention and you answer this question in the document, when you turn it in, you answer this question, then, and show me your work, because this is a key and you can see the answers, but you got to show me your work. You got to prove to me that you arrived at that calculation. Then, I'm going to show you how this calculation is done to answer the question, and you'll use a similar method to that to calculate the experimental molar mass of benzoic acid. That's the objective of this experiment. And then once we get that value, we can compare it to the accepted value for benzoic acid and see how close you are to it. We can actually quantify how close you are to it. Percent error. You should remember how to do that because we did that in our lab techniques exercise. All right. We're down to 70. All right, so when it reaches 60, we'll start taking temperatures. Still pretty warm. Yes, indeed. It's on its way down, and we're getting ready to take our first 2 measurements before I write them on the board. Okay. 65. Stirring also keeps the warm liquid not only equilibrated, but in contact with the cooling walls of the container. So that's how we evenly distribute the loss of heat in this process. Almost there, 63. And then we'll start measuring and writing on the board. Okay. 62. 61. Almost there. And go. So that's 60 degrees at time 0. And at 30 seconds, we will take another measurement. "20 seconds. All right. 8, 9, 58. So we're at 60. And 58. Now, almost there. 5 seconds. Take another measurement. And that's 56.5. Okay, now 1.5 minutes is our next measurement. There it is. And we're at 55. 55 degrees. At 2 minutes. Here it comes right now. 53. At 2 minutes. And 2.5 minutes. I think the reason it's not cooling as fast as in past experiments is there's just one of me, and I can't be stirring and writing at the same time. Here we go now. 51.5. Coming up on 3 minutes. 180 seconds. Here we go now. 49.5. Another 30 seconds coming up in 5. And that's 48.5. Okay. Coming up at 4 minutes, 240 seconds. And that's 47. 47 degrees. Let's see, 47. Next measurement, 45.5. 45.5 degrees. Okay, next measurement, 300 seconds, which is 5 minutes. Here it comes, and that's 44.5. Okay, we're getting close to the former freezing point. But we know that the freezing point is going to be less than that. So we're just going to keep an eye out for crystals. Here comes the next one. 43. 43. Okay. 6 minutes coming up. 360 seconds. And this is 42. Okay. Ten seconds to the next one. I thought I saw a crystal, but I don't believe so. 41. Because the temperature's still dropping, and I think I knocked a piece off of the walls. 41. 7 minutes coming up. 3, 2, 1, 0. 40. Okay, we're still dropping, and I don't see any crystals yet. Like that. We're getting very close, very close, very close. Next measurement. 39. Still dropping. Yeah. Next measurement. 2, 1, now. 38. 38, still dropping. 38. I think I see something happening here. Yeah. It's getting cloudy. Let's see if this one holds steady at 38. Yep. 38. That happened quick. Very quick. Okay. So if we get another one at 38, we'll call it quits. Coming up in 5, 2, 1, measurement. 38. We're there. Okay. So we don't need this one, or this one. And this is our freezing point. I think because these three are the same, that this should be our freezing point, 43. So 43 for the pure lauric acid, 38 for the mixture. So what's the difference? Well, obviously 43 minus 38. 43 minus 38 is what? 5 degrees is the difference. Now, when you do these calculations, you actually only need the, of course, a decrease in temperature is a negative change, but, and of course, I've always told you that it's final temperature minus initial, so it should be 38 minus 43, but we're going to take the absolute because the only thing that matters here is the magnitude, 5 degrees. So now 5 degrees C is equal to the concentration, the molar, actually the molal concentration, I'll define that in a second, the molal concentration times the freezing point depression constant for lauric acid, 3.90 kilograms degrees C over mole. Okay, what is molality? Well, we know what molarity is, right? Molarity is moles per unit volume, and that volume is in liters. Right? Molality, and this is liters of solution. Molality, the little m, is moles of the solute in kilograms or mass. Right? Well, I shouldn't use that because it gets confused with the little m here. So let's just say per kilogram of solvent. Okay? That's molality. Now, why do we use this one and not that one? In fact, that's one of your questions that you have to answer. Think about it. We're measuring a change in temperature, right? What happens to liquids when you change their temperature? They change volumes, don't they? So if we use this one, the volume would never be constant. Whereas if we use mass, the mass does not change with temperature. So that's why we use molality. And notice that this term here is the inverse of molality, moles per kilogram, kilograms per mole. So that means whatever the value here in molality is would cancel that, except that we don't have a value here. This is our unknown. So we keep this one. I'll show you the calculation in just a minute. But now, what do you do with this data if you, let's say you forgot to observe the temperature at which it froze? Well, of course, you can see from here that when it stops changing, that's the freezing point. But you can also get a more accurate picture if you plot your data. And you can do this for each one, and you plot, so what are we changing? We're changing the time, so the temperature is the dependent variable. Okay? And the time is the independent variable. So what's going to happen? Well, the temperature starts out high, 60 degrees, right? And then you mark it off in increments. And then you'll notice that the temperature does this. It goes down. And then at some point, it goes like that. If it's a real smooth break, then you can tell exactly where the temperature is. And ours is a relatively smooth. But if you have a system that has a gradual break, then what you do is you draw a line here and extend it, and then a line here and extend it, and where they cross is your freezing point. Okay, you do that for each one. Okay, now what are we going to do with our waste materials? Well, we can't very well get them out of the tube if they're solid. So we're going to lower. The water's still hot enough. Just let it sit there. In fact, I'm pretty sure it's hot enough, because you can see it melting again. Oh yeah, it's well past the freezing point. Actually, freezing point and melting point are, for all intents and purposes, the same. There are some technical differences, but at our level of investigation, they're the same. Okay, now it's all melted up. So what are we going to do? Well, you can't pour that down the drain. What would it happen if we poured that stuff down the drain? As soon as it hit the trap, it would solidify and form a plug. And then you'd have a clogged drain. So, we use a disposable container, like this plastic weigh boat. And we take our thermometer out. Now we're going to wipe the thermometer. So we take our thermometer out, like that. And while it's still liquid, we wipe that stuff off. Right. There we go. Then we take our tube out and pour it into the weigh boat. Like that. Get as much out as possible. Okay. Then when that solidifies, it's not toxic, so we can put it in the trash. What do we do about what's left in here? Well, there's just a film on the surface, which is easily attacked by something as efficient as the detergent Dawn. So we put a generous amount of Dawn in there, and then we try to get some water out of the faucet without drenching the whole bench. There we go. So we're going to let that sit. Now, it doesn't have to completely dissolve all the benzoic acid, lauric acid mixture. We just want it to release it from the glass. So there, it'll sit there. We'll just give it time to work. And while it's doing that, we'll rinse out our utensils so we can use them later on something else. Of course, this one is going in the trash. This one has been cleaned, and it's... no, it hasn't been cleaned. I remember we left that for later. There we go. Save that one. The thermometers can be returned to their buckets. And I got one from one bucket and one from the other bucket. So we return those to their place. And let's remove the hot water so that it'll cool down faster. Now, what can we do with this distilled water? That is distilled water. Well, can't use it anymore. Why? Because we've contaminated it. We put boiling chips in it. So, once it's cool enough, we pour it down the drain, clean the beaker out, put it back on a shelf. Okay. So, let's see. I'm going to pause the video. Pause the video. Okay, so I'm back. Now, let's talk about what to do with this information. We have the freezing point of our pure lauric acid. We have our freezing point of the mixture of lauric acid and benzoic acid. We've done a preliminary setup for the calculation here, and we can find out the molal concentration of benzoic acid in the lauric acid. So notice that what's our aim? We want to know the molar mass, and I abbreviate that molecular weight. Old school. So what do you need to know for the molecular weight? You need to know the mass in grams per mole. Right? So you need mass in moles of our substance, benzoic acid. That's the accepted value, right? That's what you'll compare yours with later. So, do we know the mass of our benzoic acid? Well, yes, we do. Right here. We know the mass in grams. Okay? How do we find the moles? Well, look. We're going to solve this equation for the molal concentration. What's molal? Molal is moles of, in this case, benzoic acid per kilogram of lauric acid. See where I'm going with this? We need to know the moles here to put in there. We know this from that calculation. And we know this value from here. Only that's not kilograms, is it? What would this be in kilograms? I find it's easy just to go like this. 5, 7 times 10 to the minus 3 kilograms. Right? Because it takes 1,000 grams to make a kilogram, or 1,000th of a kilogram to make a gram. So this is kilograms. So if we know the molal concentration from here, and we know the kilograms from here, we substitute a value here and a value here. Then we solve for moles, which goes over here, and we calculate our molecular weight, or molar mass. Very simple. Okay. So I'm not going to finish that one. What I'm going to do is this sample problem in the pre-lab. Okay? We're going to do the pre-lab. So I need some space. I'm going to leave that there because we need that information. We've already got the information here, 43, 38. So let me take a slow pan of this information so you be sure and get a full shot of the whole thing. We back up so you can see the whole thing. Okay. We'll just take what we've done so far in this shot. Here. And here. Now I'm going to erase everything on this side so I'll have room to do calculations. Let's just take it all out in case I need to overflow. I'm going to have to erase it anyway, eventually. All right. Now, let me get a bigger piece of chalk here. In fact, I think we have some more chalk around here somewhere. Those pieces are getting kind of small and hard to handle. Chalk, chalk, chalk. Who's got the chalk? And those are standard grade. Nope. I could be wrong. Chalk. One last big piece of chalk. If I don't drop it and break it. Okay, so our pre-lab question is designed to give you experience in doing this calculation. So if you can do the pre-lab, you can do the lab calculations. Okay, what are we given? A student has found that 7.98 grams of lauric acid froze at 43.75 degrees centigrade. So, I take it that lauric acid in this case is going to be our solvent, as in that experiment. So, the mass of lauric acid is 7.98 grams. And its freezing point is 43.75. So that tells me that they were using an electronic thermometer, more than likely, which gave them 2 decimal places. We were estimating a half a degree. Okay, 1.03 grams of benzoic acid was dissolved in this. Benzoic acid. 1.03 grams. We got them beat on the mass because we have 3 decimal places and they only have 2. Now the freezing point of the mixture, or the solution we might say, is 39.43 degrees C. All right. Now, the freezing point depression constant for lauric acid is 3.9. That's over there, right over here. Same for the pre-lab question as for our exercise. Calculate the experimental molar mass of the solute. All right. I'm going to need a calculator. And did I bring? No, I didn't bring one with me. Let me get my phone. I have to resort to my phone, which is not something that I allow my students to do, especially not on tests, because smartphones are very smart. But I'm in a bind. Okay, so we're operating on the principle of freezing point depression, and that's absolute value, is equal molal concentration times Kf. What's the change in temperature absolute value? Well, we need 43.75 minus 39.43 degrees centigrade equals the unknown molal concentration times the molar freezing point depression constant, which is 3.90 kilogram degree C per mole. Okay. So what is this value? 43.75. And 39.43. This is 4.32. 0.32 degrees C. Now, what are we going to do? I'm going to skip a step, actually combine steps. So what happens to this? If we're solving for that one, this one has to come over here in the denominator, correct? Correct. Kilogram degrees C. Okay. cancel the degrees C. Right? The numerator here, well, this is in the denominator, cancels this numerator, and then we divide 4.32 by 3.91. Come on, here we go. 3.90, excuse me, 3.90. That's 4.32, 3.90 divide. Okay, and I get 1.1077. Keep several decimal points. Now, what are the units of measure? Well, notice that this is a fraction in the denominator. And what happens to a fraction when you resolve it from the denominator? It inverts. So the moles go on top and the kilograms go on bottom, which is another way of saying this one is the denominator of the denominator is the numerator. And the numerator in the fraction is still in the denominator. So the units of measure are moles per kilogram, which is what? Moles per kilogram is molality. All right? So now we know the molal concentration of benzoic acid in this solution. What we need is the moles of lauric acid, which is lauric acid here, benzoic acid here. So how do we get that? Well, notice dimensional analysis. If we multiply this value times kilograms, of lauric acid, which is 7.98, times 10 to the minus third kilograms, right? Because it was grams over here. Grams. Do the same thing as we did before. Kilograms. If we multiply this times that value, the kilograms cancel, and we're left with moles. So what do we get? I've still got the number in here, so let me multiply 7.98 exponent, 3 change sign, times. So it turns out that we have how many moles of lauric acid? We have 8.8394 times 10 to the minus 3 moles of lauric acid. So what's the molecular weight, or the molar mass? Well, it's grams per mole. So the grams of benzoic acid that are represented by these moles is 1.03. 1.03 grams per 8.8394 times 10 to the minus 3 moles. And that will give us our molar mass, 1.03, and divided by 8.839 times 10 to the minus third. 1.165. Actually, times 10 squared, so it's 116.5. But how many degrees of freedom do we have? We actually only have 3. So this would be 117 grams per mole. I did it. I broke that piece of chalk. Okay, so that is the pre-lab question. Now, if you do some rounding in here, it's very possible that you could end up with, 116. Or you could end up with, you could end up with 116. 117 is probably as high as you're going to go. All right. Okay, it just says calculate the experimental molar mass. All right. So, that's the pre-lab question. The post-lab questions, I think there are 3 of them. Suppose your thermometer reads 1 degree higher than the actual temperature during the entire lab. How would this affect the molar mass calculation? Okay, I'll just give you a hint. If your thermometer is in error by 1 degree every time you use it, that's called a systematic error, which means it happens the same way every time. If it's high by 1 degree and you measure the freezing point here and you measure the freezing point the second time, what is that going to do to the difference? Ask yourself. Change those values. Change this one. Say this one is off by 1 degree, 44 minus 39, and do the calculation and you'll get your answer. What effect does it have on the calculation? Why is molality used? This is number 2, instead of molarity when doing colligative property studies. I told you what a colligative property is. This is one of them. Why do we use molality and not molarity? I already told you that. So go back and look at the video if you forgot. What are some possible sources of error in the experiment? Okay, just think about it. Go back and think about what we did. Where could you have error? I mentioned one of them, but that's not the only one. You know, there could be errors with the equipment, some types of errors. There could be errors that are introduced by the experimenter. I could have made errors. And if you were observing, you may have seen some possible errors. Never discount the possibility of errors that occur from reading instruments. Okay, that's all I'm going to say about that. Okay, so all you have to do is complete that exercise and hand it in on the hard copy. And that's it for molar mass by freezing point depression.